I'm going to turn it over now to Michael. Um, as David was saying, the global computational supremacy, instead of AI, I should say now, has recently brought up a resurgence of interest, by chess and Go, self-driving cars. And one aspect of this revolution that I was stricken by was a series of papers by CEOs of Tesla and Microsoft or Bill Gates and Google, writing in Science about how AI is going to take over the world and we should be wary of that. That sort of is one of the things that caught my attention, among other things, about this AI phenomenon. But I'm going to turn it over to you. Like Dave said, you've written about it in a nice article in the Harvard Data Science Review, in a piece that had several commentaries by academics, including Dave. And can you help us think through your perspective of the AI revolution, Michael?
Yeah, thanks for inviting me here. Just to say, I'd like to go through slides quickly, and I'm not the next person. I'm not hitting the button today. So whoever's doing that, be prepared, because I like to kind of move quickly. That's my style. So let me just say, I really enjoyed it so far. It turns out that I think David and I agree on the phenomenon, and we agree on where you look to try to understand the phenomenon, which is really outside of academia. It's the outside world. And so the first part of his talk, I'm going to agree with him almost completely using my own language. But then I'm going to diverge. I don't have the same interpretation of where this is going and what the right way to think about this. There's going to be a little less depressive feeling, but that's okay. I'm in Italy, and I can't get depressed when you're in Italy. So next. First of all, I don't like this phrase AI. I think David's totally right at the end. This is not about AI. This is not about intelligence of the humankind putting in the computer. It's about massive brute force data analysis and the implications of that. Okay, my view on this is that it actually is the emergence of a new engineering field. And I would not say just engineering. And we like to do science, and that's just engineering. I think that's the wrong way to think. Think about chemical engineering in the 40s and 50s. Before the 40s and 50s, there was not chemical engineering. There was chemistry, there was quantum physics, there was fluid flow. There was a physical understanding of the world at the level, amazing level. But then people thought, is it possible to build systems that do this at scale? Could I make a factory that takes in inputs and produces outputs, which are new products, new materials, plastics, new kinds of clothing, things that have changed the world, arguably more than anything we're talking about right now. And in the 40s, 50s, young people, this is what they were excited about. And to develop this field, first of all, they had to try it out. They built some factories, some of which didn't work, some of which exploded, some of which just didn't make the product. And money was made, money was lost. There was a Wild West moment. But there was also the development of a field called chemical engineering. And it really arose in that era. People both being inspired by the physics and the chemistry, but also inspired what's happening in the outside world and trying to make sense of it. And new principles were developed, new ideas, as Don was saying. It wasn't just engineering, quote unquote. It was new concepts, new thermodynamic ideas at scale. And if you become a major in chemical engineering now, you're not just learning engineering tricks, you're learning a whole bunch of mathematical concepts that were figured out. And years later, we have had a successful field that has changed the face of civilization. It's had its problems because it's a powerful technology. I know less about the history of electrical engineering, but I'm sure it's very similar. Go back about 50 years before that, there was electromagnetism, there was Maxwell's equations. What more do you need? You have everything. But then people thought, well, is it possible to electrify a city or a country? How could I bring power across vast distances? How could I bring power into a home? How do I build circuits? So principles like impedance matching, which were sort of implicit in electromagnetism, but weren't really brought out, had to be brought out so you could make modular systems and make them work at scale. And you could start to make them work at planetary scale. And new phenomena started to emerge. And the new mathematics was needed to support this. And that field is called electrical engineering. And if you get an electrical engineering degree, you know a lot of mathematics, all right? So I think that's actually what's happening right now. We have 3 centuries of inferential thinking, inferential ideas, and algorithmic ideas. I think computer science actually is not just engineering. It has a lot of real ideas in it. And if you put the two together, you start to get what we might call data science. And you start to get this planetary scale flow of data and flow of value and flow of business models. That's what we're actually seeing in the outside world. And that's just like in the 40s and 50s, people building chemical factories. We're doing it without really knowing what we're doing. Sometimes it works, and great things happen, like a search engine. Some things, sometimes, you know, cell phones work. Other times, really bad things happen, like, you know, election manipulation or fake news and all that. And we're just kind of making up as we go. And so what we need is a new field of engineering, which has its principles like impedance matching or thermodynamics at scale, that learn how to talk about human desires, preferences, and values at planetary scale with data flows as the underlying currency. So economics, microeconomics talked about a lot of this, but they never had data flows and compute. David's right about the compute, but it's not just the compute. It's the data flows and the value associated with data flows. And we need a language to talk about that, and a language for design and analysis. Next. Okay, so ML/AI is just a small piece in this bigger picture. And I'm going to move away from that phraseology. I think ML is kind of fine. But if you want to use that for terminology, you have to recognize there's two sides to it. One of them is pattern recognition, which is typically labeled data sets and massive amounts of data, and finding the patterns that allow you to sort of interpolate and in some sense narrowly generalize. And that's what the neural net and the deep learning and so on have been about. And it's become a commodity. So you have massive data sets, but also the software is available. All right, is that everything? Well, there's some people in the ML community who argue it is. You know, that if you can predict really, really well, you can do everything. I totally disagree. And there's another side of the field, which is also active. It's just less prominent. It's the decision-making side. And it has to do with making high stakes decisions, not deciding whether there's a bunny in the image or something like that. It's like, should you have a heart operation? And it's about explanations for decisions, and it's about sequences, about simultaneous, and it's also about multiple decision makers and market mechanisms. If you don't start to embrace this, and you're building systems that are helping making decisions at planetary scale, then you're not actually building systems that are going to work. Next. Okay, so if this is all true, what I'm saying, you should have seen it in the outside world. This shouldn't have been an academic invention that was somehow picked up by people and eventually led to something. It should have already been present, just like chemical engineering was present. And I think it has been. So I think the first generation was already in the 1990s. Companies like Amazon and eventually Alibaba and so on built back-end systems that could do things that humans could not do. For example, fraud detection had to be brought down to 0.01% instead of 3%. So you could do commerce on the internet. Otherwise, you couldn't have done commerce. And how do they do this? They take in massive amounts of data. They built computer farms. The origins of the cloud were there. Okay, it wasn't for AI or any of this later stuff. It was for building fraud detection systems back in 1990, right? And they did it really well, and they built systems that brought it down to 0.01%, and you could do e-commerce, okay? And humans can't do that. Even more importantly, supply chain management, right? If you're selling 1 billion products, which is what Amazon and Alibaba are currently doing, to hundreds of millions of people, you have to have a model of the supply chain that's extremely detailed and extremely accurate, extremely well calibrated, getting ships across the Indian Ocean, how long does it take, and so on and so forth. And they did that. And they did that with huge, massive amounts of data and compute, okay? So that's the area it was actually done, and that led to billion-dollar industries, and it's changed our world. So it's already sitting there. And that was a big engineering system kind of done hook or by crook, all right? The second generation to me was the human side. You realize that a lot of this data wasn't just about supply chains and ships and, you know, trains and all that. It had human data in it. And so things like recommendation systems took human transactions, preferences, and so on, and led to making predictions that help people with their decision making at scales of hundreds of millions. E-commerce, social media started to rise in that period. Same underlying technology, same underlying big farms of computer systems. Eventually, the cloud started to emerge in this era, and same massive data sets, and same sort of thoughtlessness about what it was all meant. But it led to a billion-dollar industry. All right, this third generation is what I think is happening now. It's what I would call pattern recognition. It's the deep learning, it's the speech recognition, computer vision. And I'm less impressed than David is. Okay, so translation, yes, you look at Swahili, you go into Croatian, or it's really striking. But there's zero understanding of those sentences happening. And I speak multiple languages, and I always see errors, even to this day. They don't quite get it because they're not understanding what's being said. Oh, they're copying strings to strings, or as David said, images to images. If I start to have a dialogue with one of these systems, or if I have a dialogue with David, he and I are going to build up a shared understanding of what the heck we're talking about. Maybe there's some event in the world we're talking about, it's going to happen tomorrow, and somebody's going to come and this is going to happen. I'm going to start to form a mental model of what the heck he's talking about. It's going to have social components and physical components and temporal components and all that. And as we develop this shared understanding, our language will continue to refer to the entities which are only in our head. And the systems that are doing translation now cannot even come close to that minimally. They are totally bad at that, right? So I am not nearly as impressed. I don't think we're getting any understanding. And without understanding, you're not really doing anything that's human, okay? You're doing something else. Again, it's something big. I agree with Dave there. It leads to, you could commoditize it, you can make, money, but it's not the real thing, okay? Actually, I think what's already emerging is something more interesting, which is something which is often called Internet of Things in the CS world, but that's kind of just the boring problem of putting things on giving IP addresses to everything. It's really this fact that we have flows of data and decisions across the world in commerce, in transportation, in medical care. The whole pandemic response is a ad hoc network of people flying things, data and decisions and occasionally experiments and so on, all around, hoping to damp down, like an immune system would do, a pandemic. Next. Okay, so let me dig in a little bit more to this decision-making side, because the pattern recognition side gets so much attention and people think it's everything. So let's think concretely about, you go into your doctor's office and in 5 years, and your doctor's going to measure all kinds of things about you, your heart rate, your blood pressure and so on, but also your genome, because that's going to be cheap, and a whole bunch of other stuff. So like 100,000 dimensional feature vector will go into a big neural network that has all the world's medical knowledge in it. It's a huge data set and massive computers were used. It becomes the super doctor, right? Is it actually going to be a good doctor, right? And the answer is absolutely not. So for example, one of the output units of that network will be like the heart attack output unit. And if that number is over 0.7, then in the historical data, that suggests you're about ready to have a heart attack instead of have an operation. You sitting in your doctor's office in that moment, are you going to say, yeah, oh my God, the world's smartest thing just told me I'm going to have a heart attack, I better have an operation? No, absolutely not, right? You're going to first of all say, wait a minute, what's your error bar on that? Am I just over 0.7? And moreover, where did the error bar come from? Was this data gathered last week? Was it gathered 10 years ago? What's the provenance of this data? Was it about people like me? Is it about some other people? Was it the same machines that I'm being tested on today? And so on and so forth. We're going to have a whole dialogue. Again, where a neural network is not going to be able to support that dialogue. We're going to have counterfactuals. We're going to say, if we were to try out this other, if I were to eat better, also you're going to remember things about your lifestyle that you never thought of before. That, did you know that I actually had back when I was younger, I had a respiratory problem. I forgot all about that. And the whole point is that's not in that neural network. It's not the world's best doctor because it doesn't know everything. It can't, because all kinds of things occur to people as they interact with the world around them and they think through the consequences of various things. All right, so I could go on about this, but the provenance, the relevance, the counterfactual, the dialogue, that's what real intelligence and learning and decision-making are about. And none of that is present in our current massive compute world, all right? All right, secondly, it's never about just one decision. I'm making multiple decisions today, and there are different scales and different scope. What do I eat? What do I talk about? How do I interact with my children and so on? And then it's gonna happen over days and over weeks. Right? It's moreover sets of decision that have interlocking decision makers. All of us are interlocking in our decision making, and there's going to be scarcity. We can't all have the same thing, and we're going to have to fight for it and compete. Next. All right, so let's just really be very concrete about this. Let's take pattern recognition and see how far it goes. So classical recommendation systems are a pattern recognition system, and you know all what they are. If you go to Amazon, you buy a few books, they cluster you with other people who bought similar books, and they recommend some other books that those people bought. So it's massive data in a brute force way. They become a commodity. They're on the prediction side of ML. If you use them for movies and books, you can make billions of dollars, and that's what has happened. What if you use them for other real world things where there's scarcity? Next slide. All right, so suppose I start using this commodity, this wonderful pattern recognition box, to recommend things like restaurants to people. Now, if only a few people are using the app, then no problem. They'll be very happy to get sent to nice restaurants. But what if everybody in Shanghai is using the app, right? Then by chance alone, that app, it's a pattern recognition system. It'll just pattern recognize and send 10,000 people to the same restaurant, all right? And that's Poisson statistics. It'll happen day after day. That kind of problem will arise. Or if you recommend streets to drivers because they're the fastest streets to the airport, if everyone starts using the app, then you're going to create congestion. Right? If you recommend stock purchases and everyone is using your app, you're going to destabilize the market, and so on and so forth. It's all the interactions among decisions. And here's the point. This is not pattern recognition anymore. right? I don't know which street I want to go down because I don't know how much of a hurry I'm really in until you make me think about it. And if you run an auction, I'm going to have to think about it. But before you ran the auction, I didn't have to think about it. All right. Which restaurant do I want to go to? All right. Here's where Silicon Valley and the big data, Googles and all that get it wrong. Facebook, especially. They think you're going to understand how to load balance. That, oh, 10,000 people I'm sending to the same restaurant. That's the problem. What I'm going to do is decide these 50 here go to that restaurant. These 50 go to some other restaurant. How do I decide? Well, I know enough about these people because I have all their browsing history. I have all this huge amount of data. I can know them. And I can decide which ones they should go to. And I hope you realize how ridiculous this is, but that's actually where the big data, data science people have gone. They think they can figure it out and they can't, right? Partly because I don't even know in that moment. I think, okay, I see that restaurant looks really interesting. I'd try that out, Thai food. I never had that before and so on and so forth. So really the way to think about this is we're all involved in markets all the time. We're involved in scarcity and that has to interact with the data analysis. Next slide. So the alternative to just thinking about massive data kind of in supercompute changing our world is that no, that's not right, because we have to always make decisions in the context of complex other people's decisions and scarcity and over long stretches of time. And the only mechanisms I know to do that has nothing to do with data analysis per se, it's markets. They've been working for thousands of years. They adjust themselves over time and they're not perfect. Right? And they're going to be made better and new phenomena will arise and new thinking will be needed as we put microeconomics together with statistical data analysis, because that's what microeconomics people have never done. They've had all the numbers, the preferences, the game table known, and then you work out the consequences. What if those are not known and people have to experiment like in a bandit situation? Next slide. All right, so markets are really algorithms. And this is not a very computer sciencey kind of thing to say. Computer scientists were deductive logic and they put it in the computer and then they brought in data and made it a little bit inductive. But markets are a whole other thing and we really need to have them in here. And of course, we have to work more on this. We're going to need 100 years of work on this because markets are not perfect. They have to be regulated in many ways. And that's the old style markets. These new markets that are emerging are going to have all kinds of new phenomena. Next slide. I'm going to give you a very concrete example. Music. There's more music being listened to today than ever before in history by factors of tens to hundreds. More people making it than ever before. That's amazing, all right? So you think there's this flourishing market and there's no market, all right? And data science is needed here. So what do I mean by this? Well, if you actually look at data, it turns out that 95% of the songs being listened to today in the US were made by people you never heard of and were made in the last 2 years. So it's not that the huge, Beyoncé's or whatever, that everyone's listening to them. No, kids walking around with the headphones on are listening to the latest, coolest thing, right? Well, the people who made that are probably other 16-year-olds who on their laptop are really good at making music and put it on SoundCloud. Then the computer science community steals their bits, takes the economic value out of it and streams the bits to other people, and then restores economic value by advertising against it. They created a fake market on the side of the real market they should have created, which is linking producer and consumer and making economic value flow between the person who wrote the song and the person that listened to the song. Next slide. All right, so how do you fix this? You don't have to go into super intelligence of any kind. You don't have to do anything particularly novel. You just have to do core data science. You think about data science not as doing translation and mimicking humans. You think about it as creating a new kind of market. And to start with, it's really easy. You take each person who's a musician who makes enough music that they're being listened to by people. At the end of the week, they get to see a dashboard, which is a map of the country they live in. And there's a dot every time someone has listened to one of their songs, right? And they now discover that, in Dayton, Ohio, 10,000 people listened to my songs last week. For whatever reason, I don't know why, but I'm popular there. This is just data science, no understanding. But now I can show that to the venue owner in Dayton. They can see the same data I'm looking at, and they can say, yeah, you're popular here. Let's invite you. You give a show, you make $20,000. You do that 3 times during the year, you have a salary. Okay, you're not going to be Beyonce and super money, but you have a salary. You can scale this to 1 billion people in a given country, right? Then they're also connected to their fans. There's producer-consumer relationships. They can say, I'll come play your wedding for $10,000. You'll say 5,000, I'll say 8,000. We created a market. Great things can start to happen because data now is associated with economic value. It's not just data is data and it's bits on a computer. And by the way, a friend of mine, Steve Stout, has a company called Masters, which is doing exactly this. He's got 500,000 young musicians signed to this. And the music that you'll hear on AT&T and on the NBA right now is his musicians. So this is actually happening. I've been working with Steve for 5 years on this. Next slide. All right, so the consequences of this is that AI is, or whatever you want to call it, I don't like that term, but it's data science using massive amounts of data can be a job creator, right? Because you got to create new markets, and it doesn't have to be just music. It could be like, I'm building a new house right now. I'd like some art in my house, and I'd like people to bid on my house, and it could be just anybody. It's not just a famous artist who bids on it. And if we created a connection there. So are any companies doing this other than, say, Steve Stout? Well, in some ways, like Uber is more like this. Facebook, no. Google, no. And I think those companies are not innovating anymore because they're not creating new markets. And Amazon, yes, they bring packages to people's doors, so they created a new market. And I think they're still innovating. And I think you can really put companies on the left or right. Are they creating a new market? Then they're actually also doing technological innovation. If they're not creating a new market like Google or Facebook, they're kind of not innovating anymore. And I don't see Google and Facebook actually as innovating. Next slide. Okay, so if you're an academic, are you really intrigued by working on this kind of thing? And yeah, you should be, because there's tons of new problems, all of them conceptual ones at the interface of machine learning or statistical data and econ, multi-way markets in which individuals have to explore to learn their preferences, like bandits meet markets. Large scale multi-way markets. If I'm trying to decide between 100,000 restaurants in Shanghai, there's no way I can explore all of them. I can't have preferences about them. I have to do some kind of a recommendation system to get other people's preferences to inform mine so we can start to play the game. All right, never been studied in econ, totally appropriate for the real world. All right, incentive aware classification evaluation, auctions in which preferences are learned. And then there's a lot of discussion of privacy and fairness and social good. Well, these are econ related concepts. You can't talk about that unless you talk about people's utility, and people have different utilities. And so how do we find principles for building this kind of fair system where learning is mixed with the game theory and the mechanism design? Next slide. Next. Okay, really 2 minutes just to give you a flavor for if there are any academics here. I kind of tuned this for CEOs, but just to let you say, here's a project with 2 of my students where we bring together bandits and matching markets, learning on the one side, econ on the other. Next slide. All right, here's my favorite learning problem. There's several options. There's only 3, but there could be 10,000. I don't know which one is my favorite one, so I pull one of the arms. Next slide. Just now start paging for a while. Next, next, next. So you get a reward. You pull another arm. You get a reward. Keep going. Keep going. All right, and you start to learn about these arms, and you get a confidence interval. And there's an algorithm which says pick the highest confidence bound, the upper confidence bound item. Next slide. Just keep paging for a while. You pick that arm, all right, and that has the uncertainty as well as the trying to optimize your reward built into it. And keep going, please just keep paging. So stop there for a second. So that's on the learning side, and there's beautiful theory about it. It's a real thing. Out in industry, you do A/B tests, and they're built on this kind of technology. On the econ side, there's been Nobel Prize for this, but it's really important too. In the real world, matching markets. On the one side, buyers, on the other side, sellers. You have preferences known a priori. That's what we're not going to have anymore. But if you know the preferences, there's algorithms like Gale-Shapley which match things. Next. All right, so what if we put these 2 together? What if we have, next slide, on the one side, multiple agents, and they're competing with each other. They're both trying to learn about which is the best arm. All right, next slide. But from time to time, they'll both pick the same arm. And we have an econ model there, scarcity. Both of them can't get that arm, sorry. So what's going to happen? Next slide. The arm has preferences back on the other side, the left side of the market. And so it's going to say, I prefer the bear. I'm going to give the bear the reward, and the human gets no reward. And now you ask, how do the humans behave in this situation? And there's new algorithms needed. And next slide. We developed such a market, a bandit market algorithm. Next slide. Next slide. Let me just skip this. I wanted to say you can do, there's mathematics here. You can do new notions of regret. Next slide. And you can have an algorithm. It's Gale-Shapley meets upper confidence bounds. And you can tell agents how to behave in very, very large scale markets. So the overall system actually learns and people get what they want. Next slide. Here's the piece of mathematics that says, how do you do that? And here's a penalty. It's a statistical bound, but it has an econ penalty in the denominator. Next slide. Okay, so my last little section here, take about, most 5 more minutes, is that I want to now pop up a little bit to the next level, back to kind of the real world, not just academics, and think about how to build the future, if you agree with my perspective here. Well, first of all, it's very much industry academic partnerships. All right, so the real problems I think are mostly in industry. And if you go out there, they had the word data science long before academics did. And also you need new distributed software platforms because there's no way you can build an engineering discipline without them. And these arise in academia. That's actually the open source movement has made that happen. No one buys software from companies anymore. And then startups are the critical bridging role between these two things. Next slide. So I'm just going to mention a project with a bunch of colleagues at Berkeley where we've built a platform called Ray, which is being used at Amazon. It's being used at banks. It's being used at Alibaba in China in production. We did it as academics. And it basically is an econ data science platform that allows you to run on massive computers, the kind of things Dave was talking about, econ related data science problems. We created a company called AnyScale that does this. And the previous company that my colleague Jan Stojka did called Databricks is now valued, I think, at 13.2 billion. It didn't do any econ stuff. So we think we have a clear business model here. Next slide. I'm going to go ahead and, should I finish in 1 minute? I want to leave time for, Ado, just tell me, okay?
Yes, you have like, let's say 4-6 more minutes. So
okay, let me try to do 4 on the lower side of that. So Ray is, the current machine learning ecosystems. This is behind what David was talking about. You have training, you have serving, you have streaming, you have reinforcement learning. The algorithms were developed on a single computer. Next slide. And then people said, oh, how do we make this be a distributed system so we can do it at this massive scale? And separate software stacks were developed for each of those capabilities. Often these were done in academics, but Google did some of them as well. Next slide. Ray says, no, let's get rid of all that. Let's build one distributed system, which is underlying, and then everything else is libraries on top of that. Next slide. And conceptually, this is actually a really, really simple notion. Python is a big success because it has functional programming and it has object-oriented programming. The big wave of activity at Google to build MapReduce and so on was all functional programming. MapReduce is functional programming. They got rid of objects because that didn't scale. Next slide. But if we're going to do things like dialogues and have massive neural nets as part of our ecosystem, but not only embedded in bigger ones, you have to have objects and functions. So Ray does exactly that. Next slide. And so 3 years of work, now there's several hundred people contributing to this, has led to an underlying infrastructure that does all the handling of objects and actors with scheduling and management and so on and so forth. Next slide. This is an example of taking a piece of software. It's a piece of Python code that someone wrote at DeepMind and trying to do hyperparameter search. And it was working fine at small scale, and they wanted to run it on tens of thousands of computers to do AlphaGo kind of things. They said, how do we do this really easily? We don't have the time to build it. Next slide. So they just added a few red lines there that made it a Ray-ready program. It could run now in Ray, which allowed it to immediately scale to any scale of computers. So you just added like 4 lines, and that was it. So next slide. Here is an example. You may have heard of Ant Group that almost had an IPO. Well, inside of Ant Group is this is Ray. And so here's an example. These programs take in on a cell phone. They featureize it. They put that in a big training, and then they serve the model back to the cell phone. As of a couple of years ago, this was happening once a day. And they spent a huge amount of engineering effort to get it down to 1 hour after like a year of work. And that increased their revenue hugely. Next slide. They then implemented it using Ray. They brought Ray in and they contributed to the open source development. Chinese people did, amazingly. Anyway, it came down from an hour to 5 minutes using Ray with no change to the software. And that was also a massive economic boom. Next slide. It's open source. Next slide, there's the GitHub. You can go there yourself right now and start contributing to it. The growth is now matching Spark. It's geometric growth. So Spark is the #1 platform worldwide, by the way. So we think we'll match that. We are matching that. Next slide. Contributors slide. Next slide. And then some of you might be, oh, sorry, that's the library on top of it right now. I want to get one more slide. Next slide. And so here's some of the companies that are actually using this in production. So the main point I wanted to make here was not so much bragging about what we did, but rather that surprisingly, industrial problems at scale are being solved by academic software. And if you haven't kind of been following that, I hope that you're awakened to this. So Goldman Sachs is using this, Microsoft, Ant Financial, Amazon, and so on and so forth. And I think the next slide is my final slide. Okay, so that's a slide I already had up there before, but I hope to prevent a misunderstanding. AI is not happening. I totally agree with Rod Brooks. The real deep understanding involving like understanding language and all that, not even close. But what we're missing and why the revolution hasn't really happened yet is not just that. That's what I was writing about in that article. But really, it's because we're not thinking about markets. We're not thinking about the planetary scale systems that involve humans and their preferences and actions and scarcity. So the only way to get us all to be happy and have value is to put all this stuff we've been talking together with microeconomics. Thank you.
Thank you very much, Michael. Very interesting perspective, lots of new information.